Welcome to this lecture on cryogenic hydrogen technology. Today we are going to learn about deuterium production. This deuterium is an isotope of hydrogen, and we are familiar with other isotope of hydrogen, that is deuterium and tritium, and of course, this deuterium production is not directly linked to our hydrogen technology for hydrogen technology for fuel, and but it is in a broader aspect. If we look at it, this hydrogen can be treated as this deuterium separation and production is of course a part of the cryogenic hydrogen technology. So, we will go to this today's concept is basically the deuterium production, and we will find that deuterium production will involve lot of cryogenic activities in it. So, let us look into it, and first of all we will these are the keywords. We will see hydrogen enrichment, then hydrogen deuterium separation, and then hydrogen catalytic decomposition. So, first of all we need to understand what is deuterium and how is it different from the hydrogen. So, in the last class we have talked about the isomers of hydrogen, and that is orthohydrogen and parahydrogen, where we have seen that those are having the same atomic mass, but they are different in with respect to their spins or nuclear spins. But here these are the isotopes of hydrogen, where the atomic mass of hydrogen is different, and they are basically, as I told you, that with the atomic mass 1 it is hydrogen, with the atomic mass 2, that means this deuterium will be having atomic mass 2, where one is the proton, the other one is a neutron. So, with this 2 it is the deuterium and its symbol is D, and there is another isotope of hydrogen, that is tritium, with the atomic mass 3, and basically this is an isotope, but with a very short half life, and we are not going to discuss about the tritium at this moment, but the deuterium separation will be discussed in this lecture. So, deuterium and hydrogen both are diatomic molecules, but in the atmosphere this hydrogen is hydrogen and deuterium is forming a hydrogen deuteride. It is again a diatomic molecule, but it is mixed, and it is available with hydrogen is to hydrogen deuteride with a ratio of 3200 is to 1. So, you can understand that the presence of hydrogen deuteride is very small in atmosphere, or natural hydrogen. So, if we have to decompose this hydrogen deuteride into its two constituent hydrogen and deuterium, we need to first concentrate this hydrogen deuteride, and then we can think of separating it. Now, this hydrogen deuteride and hydrogen normal boiling point of hydrogen, we have seen that it is 20.27 Kelvin. Deuterium boiling point is 23.67 Kelvin, and hydrogen deuteride, that is another diatomic molecule, is boiling point is 22.13 Kelvin. Now, why are we talking about this boiling point is because the concentration or separation of this hydrogen deuteride from this hydrogen mixture is needing a kind of first of all, as I said, that concentration will be necessary, and then it has to be separated from hydrogen, and then only we can decompose it into hydrogen and deuterium. Now, how to separate this hydrogen deuteride from hydrogen? It's one of the separation process is by cryogenic distillation. So, we will not go into the details of the distillation in this class, but we will talk in a nutshell about this hydrogen deuteride separation from hydrogen and how this distillation works in this in cryogenic domain. So, just I will try to briefly give you an example, like say we have a mixture of two component, say imagine that A and B are the two components which are of which A is the lower boiling point component, lower BP, and B is with the higher boiling component, higher boiling component. So, if they are mixed together and if we have to separate and if they are in liquid form, so there comes the hydrogen deuteride and hydrogen, which is available in normal hydrogen as a mixture of, say if it is 3200, this will be only 1 . So, this is the kind of ratio it maintains in the gaseous condition. This is normal hydrogen and this is hydrogen deuteride. So, if we have to separate them from this, if we have to separate this hydrogen deuteride, we first need to make a liquefaction of these two components, and obviously, it has to be brought down to the boiling point of this order of 20 K or so. Now, if in case of A and B, this is say the lower boiling point, it is having the higher boiling point. So, if this liquid mixture, if it is heated up, what will happen? The lower boiling component will try to move up and the higher boiling component will be remaining at the bottom. So, if we look it as an example like say alcohol and water mixture, we will find they are having widely different boiling point, and if you are heating it up, the lower boiling component, that is the alcohol, which will be traveling up and leaving aside the water at the bottom. So, you cannot exactly tell that the vapor that you have obtained is free from any water in a mixture of water alcohol, as I have told. So, in a AB mixture, this A which has come up as a lower boiling point vapor, it cannot be said that it does not contain any vapor in it. Okay. So, similarly, we cannot say that B is completely pure B, it can also have some amount of A mixed with it, but mostly the vapor which has come up, it will be mainly A, and which is there at the bottom, that is mainly B. Now, if we collect this vapor A from the top, again if we liquefy it or if we make a liquid of this, it will be rich in the A component at the top and B component at the bottom. Again, if we put some heat, and you will find that the A component is coming on the top. So, depending on their relative boiling point, or what we call relative volatility, what we call, depending on the difference in their boiling point, it would be easier or difficult to separate. So, similarly, as we have seen that we have separated this component A, similarly we are separating this component B, again we will put some heat in it. So, we will always try to separate them in terms of A and B successively. So, this is what is called fractional distillation, and we will find that this lower boiling component will be in the form of vapor, and it will be gradually on the top we will find it is reached in lower boiling component, and at the bottom we will find that the higher boiling component is more it will be preferring mostly the lower boiling component, higher boiling component. So, now here these two will be separated like this in a distillation column. So, I am not going into the packed bed column or the tray column in that details, but mostly what we can understand that sometime we need to heat it up and this vapor that you have collected, again it is to be condensed so that we can heat it up and generate the A and B or separate it as A and B. So, like that this distillation column works, and we can separate the its constituents. Here in this case we have the hydrogen and hydrogen deuteride. Now, in that case let us see, if we remember that the boiling point of hydrogen deuteride was around this was the boiling point of hydrogen deuteride 22.13, and deuterium is 23.67 and hydrogen is 20.27. So, they are pretty close to each other. So, obviously, what we need to understand that this distillation will be quite difficult in nature, but we will again as I said that we will not go into the details of this distillation column. Only thing is that we will assume that we have the refrigeration available around 20 K to make it liquid, and we have the adequate heat, which is not difficult particularly for cryogenic engineering. Anything which is in terms of the room temperature, it can easily pick up the heat from the room temperature, and heat addition is very simple in case of cryogenic engineering operation. So, assuming that the heaters are easily available and we have the refrigeration process available around the 20 K, we can now try to look into the enrichment process of this hydrogen deuteride and then to the hydrogen deuteride separation. Now, this hydrogen and hydrogen deuteride, this mixture will be first compressed and then it will be expanded, and a part of it will be cooled in the heat exchanger. So, I am not going into that details, but what it will give you is we will put it in the column, as I told you in a rectification column. It will be giving or separating it into its constituent, that is the hydrogen and hydrogen deuteride. So, it may not be possible to separate them in a single column. So, sometime we need more than one column. This is the primary column we call it, and then we can primary column, and then we will have a secondary column. So, from where this enriched hydrogen deuteride, say this is about 3% of the hydrogen deuteride, will be taken to the second column or secondary column, where again it will be separated primarily into HD and H2. Now, on this part, this hydrogen deuteride, it will be about 95% hydrogen deuteride, and on the top it will be hydrogen deuteride, I am sorry, hydrogen. So, this hydrogen will again be taken back into appropriate location, but what we will do is that now we have sufficiently enriched hydrogen deuteride, and we now can take out this hydrogen deuteride, though it will be in the liquid condition. We will take the vapor part from heat and then we will put it into a heat exchanger. So, in this heat exchanger, what will happen? This will be taken into this reaction, where hydrogen deuteride will be decomposed into deuteride and hydrogen. So, from here what we will try to do is that this deuteride will be taken back into another column, and this deuteride will be going back. While going back, again it has to be cooled down, and it will come over here in this deuterium column. So, this is going back to this, and here it will be separated into deuterium and hydrogen finally. So, this deuterium is in the liquid form. So, if we want it in the gaseous form, again we will put it into that heat exchanger. So, from here we will have the deuterium for the deuterium product. So, if anybody wants it in the liquid form, one can take it out from here itself. If it is needed in the form of deuterium in the gaseous form, one can put it through the heat exchanger and it will be coming like this. Now, the question is, why did we do this decomposition? I mean, why did we use this heat exchanger to heat it up? Because this reaction is favored at higher temperature. So, typically 250 to 300 Kelvin depending on its application will be it will be cooled down or heated up depending on this heat exchanger and the operation. So, particularly we will try to now look into this reaction where hydrogen deuteride is broken into hydrogen and deuterium. So, its equilibrium constant will be if it is known, we can look into this reaction, how it is giving us the two products. So, let us now look into this equilibrium composition of hydrogen deuteride. It will break into the hydrogen and deuteride. This reaction, as I told you, it occurs at elevated temperature and its equilibrium constants are known to us. So, this is the equilibrium constant. It gives you it is related to the concentration of Hd and D2 and the hydrogen. This Y stands for the composition in the vapor phase. So, this Y k E or the equilibrium constant will be known to us, and if it is known, then we can try to look at a particular problem. Say, if we remember that this hydrogen deuteride was composition in the column was 95% hydrogen deuteride and Hd, along with that we had 5% of H2. So, this 95% Hd and 5% H2 is coming here in this reaction, and then in presence of the catalyst it is going to decompose into deuterium and hydrogen. Along with that, some portion of the hydrogen deuteride will also be present. It is not like that we have taken the hydrogen deuteride and everything is getting converted into hydrogen and deuterium. So, this reaction would be something like this, and if it is, say, as I told you that 95% hydrogen deuteride and 0.05 is the composition of hydrogen, and what would be the composition of C1, C2 and C3, and that is for C1 is for the hydrogen and C2 is for deuterium and C3 is for hydrogen deuteride. So, we need to look into the composition of the gas, which is this product concentration. If we want to find it out, how do we do that? So, let us look into that part. Okay. So, this can be done by let us look into this. First of all, we can do the hydrogen balance in this equation. If we look at this is 0.95 for the hydrogen, and then it would be 0.05, I am sorry, this is not there, 0.95 plus 0.05 into 2, that is for the hydrogen on this side. On this side we have 2 C1 and on this we have C3, that is what is the if we try to make an balance for the hydrogen. So, this will become an equation involving C1 and C3. So, C3 can be written as C3 equals to 2C, I am sorry, this is 2C1 and this is C3H. So, it becomes C3 equals to 2C1 with a minus plus 1.05. So, if we add these two on this side and on this side, it would be 2C1 and C3 is equals to minus 2C1 plus 1. So, this is one equation which involves C3 and C1. Similarly, if we try to balance the reaction with respect to the deuterium, we will have let me change the color of this pen. So, this is 0.95 for the deuterium. On this side what we have is there is no deuterium on this side. So, it can be written as 2 C 2 and we have 1 C 3. So, C 3 2 C 2 like this equation would be there. Now, if I try to replace it and put everything in terms of C 1, what it would give is equals to minus 2 C 1 plus 1.05. So, this can be written as C 2 equals to it is C 1 minus 0.05. So, this is another equation we have obtained. So, altogether we will have 3 component, this C 1 plus C 2 plus C 3 and this is supposed to be 1. If we combine these 3, if we look at C 1 plus C 2 is 2, I am sorry, C 1 minus 0.05 and C 3 is minus 2 C 1 and plus 1.05. So, combined together you will find this is equals to 1 and that is equals to the Cm. Now, if we look into it, we have 3 unknowns and we have gotten 3 equation. One is equation this, one is equation this, these are the 2 equation. The third equation I am yet to tell, but already I have told about this. So, this will give you the third equation and as I said that K E would be known. In this case K E is given as in the form of ln K E is equals to 1.1848. So, that K E can be taken as 3.27. So, this K E is 3.27. In that case what will happen, we will have another equation. So, this y h d is basically C 3 square. Let us change the color. This K E that is known, K E is equals to y h d, that is C 3 square divided by y d 2, that is equals to C 2 and this is equals to C 1. So, we have this third equation given as K E equals to C 3 square by C 2 into C 1. So, now these 3 equations can be solved to find out C 1, C 2 and C 3. So, to obtain the equilibrium composition of this reaction. So, if we solve it, we will find that I am sorry, this is let me just erase it. We will find that C 1 is coming to be, this is coming to be C 1 is supposed to come as 0.288, you can try to solve it. C 2 equals to 0.238 and C 3 is equals to 0.474. So, that means when it is this reaction is taking place with this this equilibrium constant, this is temperature dependent, this reaction is taking place at 300 Kelvin and at this temperature this concentration part in the product stream C 2 is supposed to be 0.238. So, this is what is there in the product stream. Along with that you will have some amount of hydrogen present in it and a product H D will also be there. So, from here this deuterium in the column it will come back to the, this whole mixture will come back as such from the catalytic converter and it will be cooled down and again go to the deuterium column. So, this is how it takes place in actual system and with the as I told you that with the adequate refrigeration and heating we can separate it out or first of all we can enrich the hydrogen deuterium and from there we can get this deuterium. Fine. So, these are the references, so only it has been taken from the Baden's book of cryogenic system, and let us look into the conclusions then. So, we have seen that deuterium is not available freely, I mean in nature, it is mixed with hydrogen and it is available in the form of hydrogen deuteride, and that too it is available in very minuscule quantity. So, first of all, if we have to separate this deuterium, we need to have considerable amount of hydrogen deuteride present in the mixture, and that can only be done by using a cryogenic column, where I mean particularly one of the rather mostly commonly employed technique is the cryogenic distillation column. We can enrich it to nearly about, as we have seen with an example, to 95% depending on the column construction. And once we have the enriched deuterium, we can decompose it in using a catalytic decomposition. So, that will give you the hydrogen and deuteride, and hydrogen deuteride I mean hydrogen and deuterium, they will be separated, but it is basically in the catalytic reaction we have seen basically it is a mixture of hydrogen deuteride and hydrogen deuteride, hydrogen deuterium and hydrogen deuteride. So, this mixture has to be separated out again in a cryogenic column, and from the bottom product of that column would be the deuterium, and that deuterium can be taken as liquid as well as if anybody wants it to be in the gaseous form, it has to be warmed up in an heat exchanger and separated it and taken out as a product. So, this is about the deuterium production, and thank you for your attention.